unpredictable and black swan event, right? During some part.
Unpredictable? Sorry, I couldn't hear the rest of it.
Black swan events.
No, that was not my class. Not Black Swan. You're probably thinking of somebody else's class.
Okay.
Random walk was something that we discussed in the previous class.
Yeah.
Mihir, you asked the question, right?
Yes,
So,
ma'am. I asked the question.
okay, so I think you're thinking about somebody else's class, right?
Yes, ma'am. I think so. I got confused.
Okay,
That's why.
fine. So let's begin. I'll share my screen and then we can start. Okay, so the screen is visible to you all. Wait, it's still. Yeah, now I think you should be able to see it. Just let me know if you can't see it, all right? Okay, so I hope all of you are ready with our studio and yeah, I'll just close these. Okay, so today we'll work with a script just to get you prepared for the assignment itself. So just go to file and then new file. Some of you might be familiar with this. For those who are not, just go to new file and then our script. Okay. So a script opens up and you can start typing over there. Okay. So the first thing I'll do is just clear the environment of the previous variables that were there. Okay. Now I've typed this command. Now if I want to run the command, either I can select the entire command like this and then go to this option here which says run the current line. Okay, so I can run it this way. Otherwise, I can just place my cursor here at the end of the line or even here and hit Control and Enter. Okay, it serves the same purpose. The same information is given here. So you can either use this option to run the current line, selecting the entire line, or just place your cursor here and hit Control Enter. Okay. So now my environment is empty, it's clear. So I can start working on a fresh data set. If you want me to slow down at any point, just let me know. Okay. After this, I want to import my data set. So I'm using the data set that I shared with you all. Okay. So it's called Practical 1. Now to find it, just go to wherever you saved it. Okay, so I've saved it on my desktop in this folder. Okay, so I just go there and select the file and say open. Okay, now once you can see the data here in this window, in the data preview window. So here just go to time and change it to date. And then click again on this triangle, change this to numeric. Okay, so these are numbers you're telling R that this is the data and they're in the form of numbers. Then say import and import your data. Okay. So my commands have come here, I didn't type it in the script. Okay. So this is the data, it's showing me the data. I can come back to the script here. All of you have entered the data set?
And can you wait just a minute while we import it?
Yeah.
Thank you.
Just let me know once you have imported it and you're ready.
And from where did you select the import option?
Uh, See, go here to File, Import Dataset, then
Or
from Excel.
okay, done now.
Okay, I hope everyone's ready. If you're not, just let me know so I'll wait. So after this, we'll just load the library with whatever packages we want. Okay, so most of them are the same ones that you used the previous time. So just type library stats. Okay. Remember, we are just typing the commands right now in the script. We'll run it later. Okay, we can run it all together. Okay, so just load your library with stats, then FPP2, forecast, ggplot2, and T-series. So once you've typed all these, then just select all and then run it. Okay. I'm just typing a few more commands, okay, to save time, but I'll wait for you. Okay. Okay, have you all loaded till T series? Have you all loaded the packages?
After T series one, yes. Many of these we also haven't installed yet, I guess.
Okay. Now the next set of lines from 7 to 12. Okay, I think seasonal you all must have installed because we've used this earlier. But the rest, for example, time, date, time series, these, okay, just see if you have it or not, and then if it's not there, you can install it. Okay. I've already installed it, so it will show up here. Okay. So install these packages and then type these commands.
And what would be the code for installing F Basics?
Just go here, install packages, and just type fbasics and then install.
Okay, ma'am. Thank you.
Okay, let me know once you finish. Okay, where have you all reached?
I'm loading the packages. I think all of them should be done by now. Just have to restart our ones.
Okay. So I hope all of you have typed these out. Now, once you've typed it out, just select all and run these commands again. everyone's done?
Yes, ma'am.
Okay. And so next, we'll just tell R that this data is time series data. Okay? So if you look at the data itself, these are residential property prices. Okay, I'll just show you the data. Okay, so this was the original data, residential property prices for India. It's an index. The base year is 2010. It's quarterly data and it's not seasonally adjusted. Okay? So whenever you're downloading your data, go through all these things. What is the base year? What is the frequency of the data? Is it seasonally adjusted? If you have the option available to get seasonally adjusted data, go ahead and download that straight away. So this is from Fred. I've shared the link for this particular database with you all. So we'll come back to this. So I want to declare that RPI is time series. Okay. So the command for that is TS, which represents time series. Then tell R what is the source of your data. Okay, what is your data set called? So in my case, it is practical one. Even for y'all, unless you'll have changed the name, it will be the same. Then tell R when exactly the data is starting. Okay, so what is the first observation? Which time period is it related to? So this is 2009 quarter one. Okay. Then you don't have to specify end because R automatically recognizes where the data set is ending. Okay, so you need not specify that, but just specify the frequency of the data. So there are 4 quarters in a year, so the frequency is 4. Okay. Now to run this command, either hit Control Enter or select the line and go to run. Okay.
Ma'am, just a doubt.
Yes.
When we are loading the data, ma'am, the first column you called it a date, and the second row, did you leave it as a double or did you make it into numeric?
Numeric. Okay, once you get more comfortable with this, many people don't type this part, data equals practical. They just type practical one. R will know that the first argument is related to what is the data set. So it will pick up from there by itself. Okay.
Ma'am, you have to specify column 2.
Sorry? Oh, yes. Yeah, that's correct.
Data
Okay,
argument.
so yeah, okay, so that's good because here we are just telling R that the entire data set is time series, but that's not true. We are interested in the second column of this data set. Okay, so just make that correction. Sorry about that. So here tell R that the data you're interested in is in the second column. So it will pick up all the rows and the second column, okay, of this particular data set. And then that's the only change here. That's the only thing I've edited. So run that command. Okay. So it will just overwrite the previous command basically. Okay, so here in this environment window, you'll see that it's telling you RPI is time series data. There are 49 observations, okay, in a single column.
Ma'am, so sorry. You've written start and then what have you written with that F out there? Frequency 4, all right.
Now, after you've done this, we'll just calculate log returns. Okay, if you want, we'll just quickly plot the data and look at it. Okay, so you can type autoplot RPI and it will show you the data. You can see there's some sort of a trend in the data. Okay. Now, instead of working with the index itself, let's work with the returns. Okay. So to find out what are the returns, you can use this command. Now this is from the package time series. That's what R was prompting you. So you want to calculate the returns from RPI or returns on RPI. Now the method that you want to use is the log returns method or compound returns. Okay, so just specify that. And you also want to convert those returns in percentage form. Okay? So just type percentage equals true.
Won't you write returns before the bracket opens?
Sorry?
Won't you write returns before the bracket starts?
I'm not sure. Here you mean?
Yes, ma'am, as a
Here.
function.
Yeah, sorry. Okay, sorry, I'm a little muddled today. Yeah. So R1, we'll call it R1 and returns. Okay. You're calculating returns since that's the name of the function. Okay. So returns on RPI method is compound and percentage equals true. Okay. Sorry, I think I'm a little distracted. Yeah. So then enter this command. Okay. Hit control enter. So it's calculated the returns here.
Ma'am, what library do we require to run this function? Returns?
Time series.
Ma'am, I've installed it. It's saying could not find the function returns.
Did you load it? Did you do this library time series? Maybe you didn't run this command. Okay.
Okay, ma'am, I'll just check with that.
Okay, now before we do anything else, did it work?
Ma'am, I am trying. We can continue. I think I did not install the package itself. I have to do that.
Okay. Okay. Fine. I'll just wait for a minute. Okay, the rest of you just look at this environment window. Okay, what do you notice here?
One value less.
Yeah, okay. So we've lost one observation because we've taken log returns. So the first observation did not have a lag or the previous value was not available to calculate the return. So we lost the first observation. Okay, in the
Ma'am,
process when you're...
this returns command is for log returns specifically?
Yes, yes. These are compound returns, so it is log returns.
Okay.
So now let's just get rid of that missing observation. You can already see it here. Okay, so you need not check again whether some value is missing. So just to get rid of that missing observation, we'll just type na.omit and get rid of that missing observation. Okay. So now if you look at your environment window, there are 48 observations. There's no missing observation right at the beginning. Okay. And once you've done this, just plot the data. I think we might need to declare that it's time series first, but let's try anyway.
Ma'am, it's showing an error mentioning as non-conformable arrays. When I'm running the code na.omit r1.
What if you followed the same code that we used so far?
Okay, ma'am. I think I may have missed out on the comma too. I might have missed out on the comma too.
Okay.
So I'll just try again maybe with that.
Okay, fine. The rest of you can just try plotting it. I think we have to first declare that it's time series. Yeah. Okay, so first let's declare that it's time series.
Or is it you have to rename that R1 as
I've just renamed it as R1 itself because I don't want to change the name. I'm just omitting that first missing observation. Nothing else is changing in the data.
okay.
If you want to change the name, you can change it. Okay, so I'm trying here. I'll just quickly declare that R1 is time series data. Okay. Because otherwise it does not allow me to plot the data. Here my time series is starting from 2009 quarter 2, okay, since we lost the first observation. Okay, so that's what I'm telling R here, that my data returns data starting from the second quarter of 2009. Frequency is still 4. Okay, so I'll run this command now. So now R recognizes that R1 is time series. Okay, so these are my log returns. Once you've done that, just plot the data. Okay.
I'm here 2009 comma 2. What does it mean? Like from the second observation we are counting.
Yeah, second quarter of 2009. Since you're using quarterly data, this means second quarter here.
Okay. Ma'am.
Okay, once everyone's reached this point, just let me know.
Ma'am, it's not letting me omit the first. I'm not sure. It's not considering it as an empty spot, I guess.
Okay, I'll just stop sharing my screen for a minute. Can you share your
Yes,
screen?
ma'am.
I'm just reading your code to see.
Deal, you have missed the dash after you have used that
R1, I think.
sign. I did the same mistake.
here, no?
Yes, ma'am.
After R1.
After R1, he hasn't put that dash
Okay.
after he has used greater than sign.
Okay. Yeah, okay. All right, so let's
Sorry,
get
ma'am.
back to my screen. Yeah. Just let me know if my screen is not visible. Next, plot the data, okay? Once you've declared its time series, then just plot the data. Those of you who have done it, can you tell me what you notice when you see this data? Does it look stationary, non-stationary? Do you see any sort of a trend, anything?
And there's a somewhat downward trend, I can see.
Yeah, okay. Does the data appear stationary or is it difficult to tell?
Ma'am, maybe it's not explosive, but it is
Okay.
heading towards zero. So maybe after a period of time, it might become stationary.
Okay. Okay, so it's a little hard to tell probably just by looking at the graph. So the next thing that we'll do before we run some stationarity tests and all that, so that I don't have to keep repeating certain commands, what we'll do is we'll select one subsample of our data and we'll leave out certain observations so we can actually forecast into the future and then compare our forecast with the actual data. Okay. So what I'll try and do now is leave out data from here. Okay, if you look at the data set, I want to leave out data starting from 2019. Okay, so that I can generate forecasts for the rest of the data set. So from 2019 onwards, later on, I want to generate forecasts and then compare my forecast, the values that I have predicted for this time series with this actual data. Okay. Now to allow me to do that, I just need to select a subsample from this time series. So from this sample, what I want to do in the next step is select data only from 2009 till 2018, okay, the last quarter of 2018, because I want to leave out the rest of the sample so that I can forecast and then compare my forecast with the actual data. Okay, so we'll do that in the next step. So let's, generally when you're doing this, the part that you're leaving out and then forecasting, it's called out of sample forecasting. Okay? If you use the entire data and then generate forecasts or predicted values, that is called in sample forecasting. Okay, because you're not leaving out any of the data and then you'll just be comparing the values of this actual data with y hat, okay, yt hat basically. So that is called in sample forecasting. But when you leave out a portion of your data and then predict into the future and then compare the actual with the forecast, that is called out of sample forecasting. So that's what we want to do after some time, not right now. So we'll just create that small subsample of data first. Okay, so generally it's called a training set, the data that you use for modeling, and what you leave out is called the test data. Okay, so training data and test data. So I'll just call this data or name this particular object train1. Okay, and then I select the subsample. So the data that I'm interested in are these log returns. Okay, so I'll take that first. That is my first argument. After that, I tell R from when I want the data to start. So I want to start from the first quarter of 2009 itself, which is my first observation. But I want to end my sample at the fourth quarter of 2018. Okay, I don't want to use my entire data set, so I'll stop at the fourth quarter of 2018. Then because my data is quarterly data, again I tell R that the frequency of my data is 4. Okay, and then run this command. Okay, you might get a warning message and just ignore it. Okay, it's just telling you that you haven't changed the start value. That's not a problem. We wanted the same start value. Oh, sorry, it should be 2, all right? It should be 2, second quarter of 2009. Remember, we are using returns, not RPI. Okay, so just run that command again.
Have you given 2018 4?
Yes, 2018 4, frequency 4. Okay, now before this, if you just wanted to look at R1 itself, you can just type this command. Okay, it doesn't matter that you're typing it now, it's okay to still run the command. Now R for me is still calling it RPI, but I know that it's R1. Okay, these are my log returns. You can look at the data. Okay. There are 48 observations. I know it's starting from the second quarter of 2009. Okay, all of you have created train 1. And then let's just plot it again.
Could you explain this train one again? I missed that. I was having bad connectivity.
What we want to do is just create a sample within this sample itself, a sub-sample from this sample. So because I want to forecast the last 9 values, okay, so here I don't want to use the entire data set for modeling. So I want to use data only until 2018 quarter 4 for modeling. Okay? And the rest of the data from 2019 onwards, I'll have 9 observations. Okay? So the rest of the data, I want to forecast or predict what the values of these log returns will be. Okay, for
Yeah, okay,
the
got
rest,
it. Got
since
it,
we are
ma'am.
working
Thanks.
with returns.
Yeah,
I
got
think
it.
you
Thanks.
understood. Okay.
Yeah.
So once you've plotted the data, you'll see it's the exact same data, just the last few observations have been left out. So now let's just check it for seasonality. Does it show any sort of seasonality? Okay, remember this data is not seasonally adjusted. So we'll just run a couple of commands. GG season plot, we've used this earlier. So here I want to check train 1, okay, my subsample for seasonality. Is the data showing any seasonal patterns? R will keep prompting you, so you can just use the prompts. It will be faster for you. Okay, so just use GG season plot. Once you have used this, just look at the plot itself. You're trying to identify whether the data is showing any sort of seasonal patterns. Okay, once you've run this command and looked at the plot, anyone can just tell me what they see. Do you see any sort of seasonal patterns?
Quarter one, the quantity seems to be lower usually, and quarter three sometimes we are seeing an increase and then a dip in quarter four. But this is, I mean, I guess the quarter one is the most important one.
Yes, but it's not very clear. That's another thing you'll notice. For example, it's increasing here, here it's decreasing. Okay? So it's not very clear what the seasonal pattern is. So let's try and use that other plot also, okay? The polar plot. Okay, again for the data, train 1. Okay. Now, once you see this plot, again, it's not very clear. If there was absolutely no seasonality, you would have been seeing just circles here. Okay. But here, since you don't see a perfect circle, in some cases there seems to be a dip here at certain points. So there might be some seasonality, okay, in the data. We can't be sure again. So it's better to seasonally adjust it and then work with the data. Okay. Can I continue or do you want me to wait?
I guess we can continue.
Okay.
Ma'am, maybe 1 minute, I guess, if someone wants to copy down the codes.
Okay.
Ma'am, just one doubt. Ma'am, you went with your labels and your labels left, and you made them true, and you are getting all the years as 2009, 2010. However, when I'm doing it, I'm getting 1, 2, 3, 4, 5. Is there any reason why I'm getting that? I've also run the train one code where I've written start as 2009 too. I am not sure why I'm not getting the years mentioned.
I don't know. I think you'll have to share your screen again. Do you want to do that or?
Oh, no, ma'am, I think I figured it out. I had not put the C in 2009, before 2009.
Okay. But you have created train 1 this way itself, specifying 2009 quarter 2 ending in this.
Yes, ma'am. I think so. Basically, I did not write that C value. That C, I just wrote start equals 2009 too. So I think it just went ahead with that itself.
Okay. It ran the command for you, but.
Yes, ma'am. I think it just used the end value or something like that.
Okay. I think it's better you run it again the way that it's been written here, just so that you don't have any problems later on. Okay, so meanwhile, what we'll do is try and seasonally adjust our series, okay, our time series. So we'll do it using that X13 seats command, okay, that we discussed in the first practical session. Okay, so the command for that you'll use is SEAS, and then after that, the name of the data that you want to seasonally adjust, the name of the time series basically that you want to seasonally adjust. And here you don't, if you're using X13 seats to carry out the seasonal adjustment, there are no additional arguments. Okay, you can just leave it at this and then run the command. Okay, so this is supposed to seasonally adjust the data. So let's try and see whether this has happened. Okay, so what we are trying to do is plot the seasonally adjusted data, which you can extract this way, final SAR1. So basically, when you're doing this, SAR1 has the entire decomposition of this time series. So it will have the trend, then the seasonally adjusted part, and so on, okay? And the irregular component. Now, I just want to extract only the seasonally adjusted component of the time series. Okay, so that's why I've typed final SAR1 here, and original SAR1 is the actual data, okay, from train 1. So I'll just run this command. Okay. So now your seasonally adjusted data is supposed to be in blue. The original data is in orange. Okay, but what you'll notice is that your seasonally adjusted data is not visible at all. Okay, because it's overlapping with the original data. So the seasonal adjustment did not really seem to have any effect in this case. Okay, maybe there's no seasonality in this data at all. Okay, so maybe that's why you're seeing this sort of a result. Once you've run this command, just let me know. Or if anyone wants me to explain again, you can let me know.
Ma'am, this function SAR1 tries to automatically detect seasonality, is that?
This is, I've created this object using this command. So this command basically decomposes the time series since we are working with returns. So it's decomposing this return series into the trend, then a seasonally adjusted component, then you have the irregular component, all the components of the time series. So I'll just plot this, then you'll be able to see it, I think. So from within this object, which has decomposed the entire time series, you can extract particular components that you're interested in. If I want the trend, then I'll type trend in brackets SAR1. If I want the seasonally adjusted part, I'll type final SAR1. Okay, so I'll just run this, then you'll be able to see it, I think. Okay, this is very strange. So the trend is flat. There's no seasonal component in the data. That's what R is telling you once this decomposition has been carried out. Okay, and only your irregular component is there. So there doesn't seem to be, or this trend is basically flat. Okay. So this shows you the decomposition. That's why we are seeing that overlap, okay? Because there doesn't seem to have been any sort of seasonal pattern which are detected using this X13 seats command. So because of that, there has been no seasonal adjustment and it's simply overlapping with the original series. Okay.
Last time you used a I think decompose command. That also
Yeah.
gives the same result.
But that is an old technique. That's why it's better we
Okay.
don't use it. It's
Fair
the
enough.
classical decomposition technique, and today everyone uses either X11 or X13. So it's better to use those techniques.
Madam, one more question, maybe
Yes.
silly, because if you the same data, if we take the logs and then do just a differencing, would it give the same result?
Which data are you talking about?
The
The
original
returns or index?
the original data you take,
Hmm.
use a log form.
Okay.
The difference again gives you the returns, right?
Yes, yes.
Okay, just wanted to confirm. Thanks.
We did the same thing, but we used a command within R itself. You can do it manually also if you want.
Yeah, I did that last week or so. So I'll just compare it and see.
Okay. I think
Thanks.
I'd asked you all to do it. Yeah. So
Thanks.
we'll just seasonally adjust using X11 also and see if there's any sort of difference. Okay. So again, the command is cease. So this object is going to do the decomposition of the time series, this time using X11, which is a different technique for seasonal adjustment. So the data that we want to seasonally adjust this time is train 1, and the technique that we want to use is X11. So to specify that you want to use X11, just do this. So R will understand that you want to seasonally adjust train 1 using X11. Okay, this time let's plot this again. The same plot, is it? No. I think I didn't run the command. Okay. So this time if you plot the decomposition, you'll see some sort of very weird trend. And there seems to be some sort of a seasonal pattern which R has detected using the X11 technique. Okay, especially this pattern, we see it towards the end of our time series. This sort of seasonal pattern. Now we'll just run this command again. Instead of typing the whole thing, you can just copy it. Okay. This time instead of SAR1, just put SAR2 and then run the command. Okay, so if you've been able to generate this plot, you'll see that this time there's no overlap because using X11, R has detected some sort of seasonal pattern. So there's no overlap here. Okay. Now, since X13 is supposed to be the more advanced technique, we'll stick with X13. Okay. You can use one more command if you want, where you're comparing X13 and X11. Sorry. So this just helps me compare the two seasonal adjustment techniques graphically. Okay, you don't have to do all these things when you're doing the assignment, but you might want to use one of these techniques for seasonal adjustment. If you use if you want to use X11, you can use that. If you want to use X13, you can use that. Okay, so here what I'll do is I'll use the X13 seasonally adjusted time series itself. So I'll just call that SAR. Okay. So I'm calling the seasonally adjusted component from that object, okay, and designating it as SAR. And I'll be using this for modeling henceforth. Okay, so you'll notice that SAR now has 39 observations. Why is that? Why do we have 39 observations, not 48, not 49?
Ma'am, you removed 9 for using for forecasting.
Yes. Okay. So we left out 9 observations so that we can do out of sample forecasting. That's why we have only 39 observations. Okay. So at this point, we'll take a quick break. It's 3:35. We'll just take a break for 5 minutes. After this, we'll use certain packages for testing unit roots and stationarity. So we've already loaded those packages. After this, we'll begin unit root testing. Okay, so we'll just break for 5 minutes, meet at 3:40.
Ma'am, I have a doubt regarding the assignment.
Yes.
Do we have to just use like a macroeconomic data, or we can use data like temperature over the years or something?
Yes, you can use temperature over the years, you can use birth rates, death rates, fertility rates, any of these things, then the incidence of certain diseases and so on. For example, I came across a paper on dysentery in China, which has dysentery or diarrhea or something, which has been modeled using ARIMA modeling. Okay, so even for diseases and all that, you can use ARIMA modeling. So temperature also you can use anything.
Okay, ma'am. Thank you.
Ma'am. Hello, ma'am.
Yes, I can hear you.
Ma'am, apart from ARIMA, what are the other time series forecasting techniques that we can use, and what are the advantages of ARIMA over that?
You have VAR models, all those things we'll be learning later. Probably next week we'll do VAR modeling and so on. So there are
Okay.
lots of techniques. You also have non-linear models, but for forecasting purposes, generally ARIMA modeling is used. Then there's exponential smoothing and so on. That's not part of our syllabus, but I can give you some material so that you all can go through that also.
Okay, sure, ma'am.
Advantages of ARIMA is that one simple thing is that you're using a univariate time series, so you just need data on one variable. Okay, so you're in terms of how time consuming it is to collect the data, your problem is simplified greatly. Then you're exploiting all the information from ARIMA, I mean the autoregressive and moving average components of this particular time series. So that way, ARIMA modeling is very simple and in some sense also atheoretical, you can say. Okay? So that might be an advantage in certain circumstances. In certain cases, it will be considered a disadvantage because you're not using certain theory to explain what you're modeling or what you're seeing in your data. Okay? So in that sense, it's a disadvantage. But advantages are in terms of, I think, simplicity, then how much data you need, and probably the ease with which, compared to other techniques, you will find that it is less somewhat complex. Okay, in terms of where models and so on have greater degrees of complexity. ARIMA model is somewhat simpler compared to that, but again, it's an art and not a science. You won't get it right the first time. It will be a little bit of a trial and error process. Okay,
Okay, ma'am. Thank you.
okay, I'm just stepping away for a minute. I'll be back. Okay, so I am back. I hope you all are back too. Let's begin the whole process of testing for stationarity of a unit roots. Okay, so for this purpose, we'll be using different packages. So there are 3 different packages which have these tests. Okay, so you can use any of the commands from these packages. I'll go through all of them because each one of them has something different. Okay, that's the reason you have so many different commands for the same thing. We've used a couple of them already. We'll just go through that. Okay, so the first, later on, I'll share the script with you all. That time I'll add more comments. Okay, so the first one is from the package URCA. Okay, so this is basically for unit roots and co-integration. So you'll have a lot of tests and functions related to these topics, unit roots and co-integration, The second part we'll be studying later. Okay, so we are using this package first. We've already loaded it, so don't load it again. So we'll use this and use certain commands from this package. Now, if you want, let's see this here. If you want to check the commands from any package, what you can do is, okay. So instead of typing help, you can just type this. Okay. Okay, so if you go to this help window over here, you'll find that it's directing you to the particular package. Okay, so there are various such commands here. Okay, within this you could try specific commands. For example, if you want the Dickey-Fuller test and so on, you can just type that particular command. You might have a vague idea of what it is. Now, generally, what I used to do earlier, and I still prefer to do, is I download the PDF. Okay, so if you just go to Google and type CRAN R package and the name of the package. For example, if you type URCA, you'll be able to go to the page for the package, and then I generally download it so that I can refer to it anytime I want. But you need not do that. Okay, so the commands that we are interested in are here. Okay, so this performs the augmented Dickey-Fuller test or the ADF test, okay, unit root test. So the command is given here. The reason that I like to go and look at it in detail is because it tells you exactly what each part of the argument represents. Okay, so here first you'll put ur.df, which means you're using the ADF test, then the particular time series that you want to test for a unit root. Okay. After that, if you want a model with a trend, okay, then you can select type trend. If you want one with only a drift, then you can select drift. If you don't want drift or trend, if you want a simple AR1 model without any intercept, without any trend, then you can just select none. Okay. Then if you're choosing the trend option, it always adds the intercept. So you can't choose only the trend. It will have drift plus trend if you choose the trend model. If you choose the drift model, you just have the drift or the intercept. Okay. Then lags is for how many lags of the dependent variable you're including in the ADF regression. If you just go back to the notes that I shared from the previous class and you remember the equation, okay, how the test is carried out, you will understand what I'm talking about here. Okay, so these are how many lags of the dependent variable are included. Now, either you can specify it yourself. For example, if you want 1 lag of the dependent variable, you can type this part out, lags equals 1. Otherwise, you can allow R to select the number of lags based on certain criteria, like AIC, Akaik information criterion, or this Schwarz-Bayesian information criterion. Okay. So either one of these criteria you can choose, or if you choose fixed, it means you are specifying the lags and you'll have to type lags equals some number and then select lags equals fixed, or you can just leave it. Okay. So all this information is given over here. For example, it says if it is set to trend, both an intercept and a trend is added. So you know exactly what you're doing when you're looking at this particular PDF. Then they also give you certain examples. Okay, you might not be sure how to enter the command. So generally R will give you certain examples and you'll know how to use the command. Okay. So this particular data has been used. You can see how it has been used. Okay, so here y equals LC, that's the name of the variable. Okay, you don't have to type y equals LC. You can just straight away type the name of the variable. Then 3 lags of the dependent variable have been included. Then the model includes the intercept as well as the trend. Then to look at the results from your test regression, you'll just type summary and this part. okay, where you have stored the results of your ADF test. So we'll just carry this out. So if I just type the same thing here, you can do this. Just type 2 question marks and type URDF. Okay, the same thing will come here. Just a minute. Yeah. Okay, so it's here. You can select this. It brings up the R documentation and you can directly see this in the help window. Okay, you will not need to open a separate PDF or download the PDF and look at it. Okay, again, the example is also visible here. So we'll use this particular test first, the ADF test, and then run our command. So first let's go back to plots. Okay, so this is the time series. Now looking at it, you'll notice that there's some sort of a downward trend, right? Okay, in the time series. So first what we'll do is we'll include or we'll select the model type as trend, okay, assuming that there's some sort of a trend in this time series, and then we'll run the results. So I'm calling this object where I'm going to store the test results as df1. Okay, if you've already chosen this name, just name it as something else. Then the name of the time series that you want to test. So here we are using the seasonally adjusted time series. Okay, so we need to use SAR, which is from the trained data set itself, but it has been seasonally adjusted. Okay. So here we are using SAR. Then for type, okay, if you go to the help window again, if you've forgotten the command, type we'll choose. Oh, sorry. So we'll choose trend, okay, because we want to incorporate a trend in our model. Then let's just allow R to select the number of lags. Let's not select it ourselves. Okay. If you want to select it yourself, you can go ahead and select it. Generally, if you want to select it yourself, what you'll need to do is plot the ACF of this time series and then look at the plot and see how many autocorrelations are significant and so on, and choose the lags, okay, ACF and PACF. So lags, I'm going to choose AIC here. Since it's a small sample, I'm choosing AIC, okay, and I'll run this command now. Okay, now it's just run the command. No results have come because I've stored the results in this object. So I just typed summary and df1. Okay. So that will give me the results of the ADF test. I'll just wait for you all right? Let me know once you've finished, once you've been able to generate the results.
Ma'am, this final command in that SAR comes from which package? Again, my R got hung, so I have to go back.
This one, is it? The one I'm highlighting now?
No, before that, SAR, you define it as final of SAR1.
This is from seasonal. The package seasonal, we've already loaded it.
Yeah, no, but I had to reload everything. Thanks. Okay, thanks.
Ma'am, why aren't we using ADF.test?
Because that is from another package. I'm going package by package, okay? We'll use that
Okay,
also.
ma'am. Okay.
So, have you all finished generating the results? Okay, just let me know once you're finished.
Can you show your script once again, madam, please?
Yes, just a minute. Okay, have you all been able to generate the results?
Yes, ma'am.
Okay, can anyone tell me what the null hypothesis of this test is?
Series is non-stationary.
Yes, that the series is non-stationary or has a unit root. Okay, now if you look at the results, you will find that this is the particular part we are interested in. Okay, Z lag 1, the first lag of your time series. The intercept is significant, which means the drift term is significant. Then even the trend part is significant. Okay, and even gamma, which is the parameter we are interested in, okay, that is also significant. Now, if you look at the value of the test statistic, okay, this is the value of the t statistic attached to gamma here. Okay, so this is your basically your gamma coefficient from the test, okay, which is associated with the first lag of the time series. So here you have to compare this with the critical values for the test statistics. Okay? Since we have used the model with the trend, it has given you the tau 3, okay, for the critical values. All this I've discussed in the previous class. So if you're using a model with the trend, you'll have to refer to the tau 3 critical values, okay, or tau, in that case it was tau, okay. So here you'll be referring to tau 3, okay, which has critical values for the model with the trend. Since the value of your test statistic is greater than the critical values, okay, so you will be rejecting the null hypothesis of a unit root. Is this clear to everyone? At the 1% level, 5% level and 10% level of significance, the value of your test statistic is more negative compared to the critical values. Okay, it is greater than your critical value, so you are going to reject the null hypothesis. Okay, so I'm just writing this here. This is the conclusion from our test. Reject the null hypothesis, okay, which means our time series is stationary. That is what this test is telling us from the package URCA. Okay, now I have some suspicion that it might be a drift. Okay, if you look at the plot, I have some suspicion that this might be a drift and not really a trend component. So we'll also check it for drift, okay, just to be on the safe side. If you all have any doubts at any point, you want to ask any questions, please feel free to do so. So this time, instead of trend, I'll just specify drift. Okay, so if I want a model with only the drift, no trend, I will select this option for type. So I'll just change that here. Just copy the command and then edit it. Okay. Everything else remains the same. I've just changed the name of the object to df2 now. Okay. So now run these two sets of commands. Okay, this time I want somebody else to interpret the results for me. Yes, anyone? Compare the value of the test statistic, that is basically this gamma coefficient, that the t value of this with the critical values. Okay. Here it is tau 2 since you have used only the drift and not the trend. So can anyone give me the interpretation of the results? Are you all still typing the commands or you all have got the results? Am I audible to all of you?
Yes, ma'am.
So why isn't anyone interpreting the results? It's fairly simple. I just want to make sure that you've understood. I'm sure many of you have, so anyone can just interpret the results.
Won't we reject the null hypothesis?
What is the null hypothesis? It's still that the time series is non-stationary or has a unit root. Okay, so this is a left tail test. Okay, so you want the value of your test statistic to be more negative than the critical values for you to be able to reject the null. Okay. At least can you tell me what the problem is? Why you all are not answering? You all think it's a silly question or you all haven't understood?
Ma'am, I was a little confused on this. Test statistics is -306 and your tau at 1% is -358, right? So if the test statistic is more than tau in terms of absolute value, you have to look at true value, right? Here you don't look at the sign.
No. See, that earlier when we were discussing the coefficients from the ARIMA model, that was a two-tailed test. You're just checking whether that particular coefficient should be there in the model or not. So your null hypothesis, for example, was that A1 is equal to 0. So that was a two-tailed test. Okay. So that's why I had asked you to look at the absolute value. But this is a one-tailed test here. It's a left-tailed test. So that's why here you'll compare the value of your test statistic here, the one that I'm highlighting now. Okay, this value, including the sign, you'll compare it with these critical values. Okay, you'll look at tau 2 here. This is the critical value at 1% level of significance, critical value at 5%, and critical value at 10%. So now if you are able, I mean, the only way you will be able to reject your null hypothesis is if the value of the test statistic is more negative compared to the critical value. Okay. So now can you all interpret the result and tell me? See, for a right tail test, you're doing it the same way. The value of the test statistic has to be greater than the critical value. So here it should be a more positive number compared to the critical value. Since it's a left tail test, it has to be a more negative number compared to the critical value. If it's a two-tail test, you look at the absolute value.
So here you cannot reject the null
At what level?
at 1%.
Yes, at 1% you're not able to reject the null hypothesis, but at 5% and 10%?
Yeah, that you can.
Okay. Have the rest of you understood? Okay, I really don't know why nobody is responding. So I'll just enter this information here. Since the value of the test statistic is 3.06939, here it is obviously greater than the 10% value, more negative than the 10% value, more negative than the 5% value. Okay? But it is less negative compared to the 1% value. It is smaller than the 1% critical value. So you will not be able to reject the null hypothesis at the 1% level of significance, but at the 5% level and 10% level of significance, you can reject the null. So I'll save that in my results. Okay. So I've saved these test results. Then after this, we'll just look at the Phillips-Perron test, the next test that we had learned. So again, if you want to bring up the commands for this, you'll just type ur.pp, okay, which will bring up the Phillips-Perron test results. I mean commands. So again, you can look at the documentation to see how you will enter your command. Okay? If anyone wants me to stop at any point, if you haven't understood anything, just let me know. So this time I'm storing my results in PP1. Okay? And this is the Phillips-Perron test on the time series SAR. Okay? Then the type of test that I want to conduct. Okay? If you're using the trend, then you will use Z tau. Okay? If you're using the constant part, you will use Z alpha. Okay? So first I want to use the model with the trend itself. Okay, so this incorporates the intercept as well as the trend. Then for lags, I'll use short. Okay, so R uses a particular formula for this. You can see it in the documentation again. I think it's given in the next, for KPSS, I think they give it. But basically, it's something like 4 into T by 100 or something like that to the power 1 by 4 or something like that. If you use lag short. Okay, so it's some formula like that where you're using basically lesser number of lags based on something known as a Schwartz criterion. Okay, so here, since my data set is small, I'd prefer to use fewer lags. So I'll select lag short. Okay, and then run the command. Okay, now this doesn't show up the results again because it's stored in the object pp1. So again I typed summary and pp1, run this, and then I get the critical values and the value of the test statistic. Okay. So this time, can you all interpret the results? What is the null hypothesis? Somebody please interpret the results. Okay, some of you might be thinking that anyway the number is negative, so even if I use the absolute value and compare, you will still be right. Okay, but remember it's a left tail test. Can anyone just interpret the results this time? Some student preferably. What is the null and what is the result of the test? Here you will find that your gamma coefficient is actually insignificant. Okay. At least can you all tell me what is the difference between ADF and Phillips Perron test? How are the two different? If you don't remember, just say so. Okay, again, no response. So I'll just interpret the results myself. So here the value of the test statistic is minus 73831. Okay. Here you can see that it's more negative than the 1%, 5%, as well as the 10% critical values. So here also you're rejecting the null hypothesis. So the null is that the time series has a unit root or is non-stationary again. So in this case also, we will be rejecting the null. Okay? And the time series is stationary. That's what we find. Okay. Now next, since you all have understood how to carry out the test, I'll skip the part with the drift, okay? And we'll move straight to KPSS test. So for this, you'll type the command ur.kpss. So again, we'll pull up the documentation for this. So this time the null is that the time series is stationary. Okay, you would have remembered this part, I think. So let's just call this result T1. Okay, let's call the object T1 here. And then the first argument will be the name of the time series again, the type of test based on whether you want to include the constant term or the trend. Okay, so if you want to include the model with the trend, then you will type tau. Okay. Then again, lags will choose short since we have a small data set. and then run the command. Okay, then type summary T1, that will give you the results from your test. Okay, so if you look at it, there's not much information given here for this particular test result. Okay, but what you will find is that the value of the test statistic is quite small here. Okay, so because of this, you fail to reject the null hypothesis at all these levels of significance, whether it's the 10% level, 5% level, or even the 1% level. Okay, so you fail to reject the null and you conclude that the time series is stationary. Okay. So I'll just type that again in my results. Okay, and you're concluding that the time series is stationary. Now, just to check again, okay, I just want to check with the drift again, since this is a different sort of test, which is called a stationary test. It's not a unit root test. Okay. So because of that, I just want to check again whether including a drift will make any sort of a difference. I'll just copy the rest of it from here. Now, whenever your code is wrong in some way, okay, generally R will prompt you. There'll be a red cross mark which keeps appearing here. For example, if you missed a bracket or some comma is missing, full stop, some particular aspect of your code is wrong, then R will prompt you. There'll be a cross mark here. Okay. So this time I'm changing it to mu to indicate that I want to include the drift part. Okay. So I'll run this command. Now the results are stored in the object T2. So I'll just run this command as well. Okay. Now if you look at it this time, the value of the test statistic is 0.821. Okay. So this time you're getting a different result. So I kept having that suspicion that there's some sort of a drift here, maybe. So once you include the drift component, you find that you are rejecting the null hypothesis at 10%, 5% as well as 1%. Okay. So I'll just write that down in my results. Okay, so you're rejecting it at all the levels of significance which have been mentioned over there. Okay. So from using this package URCA, from the ADF test, your conclusion is that the time series is stationary, except only here in the model with drift, you could not reject the null hypothesis at the 1% level of significance, which is somewhat important. Okay. Then if you use the Phillips-Perron test, you found that the time series was stationary. For KPSS also, generally you're finding the time series is stationary, but for the model with drift, you're finding it is non-stationary. Okay. So next we'll move on to the other packages. Okay. So we'll use T-series next. So you all would have noticed that we have used these commands earlier. Okay. So I'll just type it here. So this again produces the documentation related to this. So we'll use this. How is this test different? Here the options are somewhat limited. This is what I was saying earlier. In the case of the ADF test, if you use it from the T-series package, okay, you'll find that you're not able to specify whether you want to include only the drift or no drift and trend. Okay, so the basic model that they are testing is one which has the drift as well as the trend term. Okay. So if you're sure that your time series has the drift as well as trend, then you can straight away use the ADF test. But if you're not sure, you might want to use the commands from the URCA package. Okay. Again, you can allow R to choose the number of lags here by itself. Okay, so it will use it based on the number of observations, your sample size. You can allow R to use the value itself. Okay, otherwise, you can also specify the number of lags that you want. So here we'll just look at this particular test, how to use it. We've done it before. Okay, so let's call this DF3 here. Okay, so this is the ADF test. The time series we are interested in is SAR. Then alternative, you need not specify this, but just to be clear that you're specifying that the time series is having the null hypothesis of non-stationarity and alternative of stationarity. Just to make sure that you're specifying this, you can also specify the alternative here. Okay, so run this command. You're allowing R to choose the lag length by itself. Okay, then type summary df3. Okay. Okay, so it does not allow me to look at the summary of results. Instead, it's just giving me a list of objects that are stored in df3. Okay, so instead I'll just type df3 and hit control enter. So this will give me the results. Okay, so here the p-value is quite high, which means I'm not able to reject the null hypothesis. Okay, so you fail to reject the null hypothesis using the ADF test from the T-series package. Okay, and the number of lags they've selected is 3 here. Okay. Suppose there were 0 lags, it will simply reduce to the Dickey-Fuller test, not the augmented Dickey-Fuller test. Okay, so I'll just save these results here. This is model with trend. Okay, that's how the command itself is specified. There's nothing you can do about it here. Okay, so here you fail to reject the null. So next, you can't play around with this command any more than that. Okay, so next, what we'll try and do is look at the Phillips-Perron test using the T-series package. We'll quickly finish this part related to the stationarity, and then we'll continue in tomorrow's class. Okay, so Phillips-Perron test is here from the T-series package this time. Okay, so again here you can specify the alternative hypothesis. You can specify whether you want to use T alpha, which is the model with trend, or you want to use Z alpha. Okay, here it's better to use T alpha because this tests gamma. Otherwise, this Z alpha, it simply tests A1 directly. Okay, gamma, remember, is A1 minus 1. So if you want to test gamma, then you will use T alpha, okay, as your option. Otherwise, if you want to test A1 directly, you can use Z alpha. So we'll use this command. I'll just type this here so that it produces that documentation related to the test. Okay. So the documentation has come here. And we can refer to this and run the test. So I'm calling this PP2. So the command that I'll type is pp test, then SAR, and then specify the alternative hypothesis. Then the type of test, we are going to use Z alpha. Okay. is select the smaller number of flags and run the command. Okay. Now they're already warning you that the p-value is very small, so you know that you have rejected the null here. Okay. So you can check summary pp2 for the results. Here you need to run this command. Again, I'm facing the same problem. So here for these tests from T series, you'll just type pp2, okay, or the name of the object, and that will produce the results. So here the p-value is 0.01, so you're rejecting the null hypothesis. Okay. So here again, if you look at it, you are not able to specify whether you want a drift or trend, which particular model that you are interested in. Okay, so the options are somewhat limited when you're using commands from the T series package to test for unit roots. Okay, so again, I'll note down the result here. So this was the model with trend again. Okay. This time it is reject null. So I'll just edit it directly. So you're rejecting the null that the time series is non-stationary, and you're concluding that it is stationary. Okay. Okay, but this you are concluding that the time series is non-stationary here. Okay, this one. So let's come back to this. We've carried out all the possible tests using the T series package. I think KPSS is still left, so we'll carry that one out. Okay, these are the unit root tests. Now again for KPSS, I'll store it in the object T3. So here you'll type the name of the time series first. This is a command that we have used before. So if I want to check if the time series is stationary in levels, okay. So I'll just type null is the time series level stationary? That is my null hypothesis. Then I type L short equals true. Okay, R is prompting me, so I need not really refer to the documentation. Okay. So here T3, the results are stored in this. So I'll just type T3. Okay, to produce the results. So here you can see that the null is being rejected here. Okay, since your p-value is small, you're rejecting the null hypothesis of level stationarity and concluding that the time series is non-stationary. So just note this result here again. This is a particular peculiarity of this data set we are using. You might not face this problem with every data set. Okay. So in the case of the KPSS test, okay, when you're checking H0 level stationarity, okay, you are rejecting the null, okay, and concluding that the time series is non-stationary. Here the null is that the time series is stationary. Okay, just remember that. So next, just in case you want to check if the time series is trend stationary, you can also run that test. Okay, so I'll do it here. I won't include it in the script. So again, the name of the time series first, then the null hypothesis. Here you're checking for trend stationarity. That is your null hypothesis, that the time series is trend stationary. L short equals true, run the command. Okay. Then check the results. So here you are not able to reject the null hypothesis of trend stationarity. I'll just save the results here. Now based on this test result, I tried detrending the series and then modeling it, and the results were not good. Okay. So clearly this time series, either it is stationary, or if you go by some of the odd results like this one or this one here, it is non-stationary and it requires differencing. Okay, so we'll work with those results tomorrow when we discuss a little more. Okay. I'll just type this final thing. When you're checking for trend stationarity, you're not able to reject the null. And you're concluding that the time series is trend stationary here. Okay. So we'll stop here for today. We don't have more time. So tomorrow we'll just do one more test from F units root, that particular package. Okay. We'll look at what is the difference. I think there's just one test in that. All right. So we'll continue tomorrow. If you all have any doubts or questions, let me know. I'll share this script after tomorrow's class. All right. Okay. Thank you for your time. We'll meet in tomorrow's class.
Thank you, ma'am.
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 Thank you, ma'am.